Hello, and welcome to our second project for physics. For this, we chose to do problem 2 about boxes. In this problem, we are presented with two boxes of different mass on a level, horizontal, and frictionless table. On the left side of the table, we have a blue box with mass m sub b, which is in contact with a spring, which has a spring constant k, that is compressed by distance x sub I. The problem tells us that the blue box starts from rest and begins moving right until it collides with the red box with mass m sub r. The now stuck together boxes slide to the right edge of the table, where they encounter a spring identical to the one on the left side. We are to determine the maximum distance that the spring on the right side compresses. We know that the table is frictionless. The blue box is in contact with the spring with constant k. The spring is compressed to a distance x sub I, which is equal to rest. The blue box collides with the red box. The potential energy is zero when there is maximum kinetic energy, and the red box is initially at rest. Our unknown is the maximum distance the second spring compresses. Another important part to understand and plan for the problem is to identify assumptions. With this problem, we assume that it is an ideal massless spring, that the system is frictionless, the potential energy of the system is zero when x is at equilibrium, and that it is inelastic. The kinetic energy
of an object is a form of energy that is due to its momentum. It is defined as the work needed to accelerate a body of a given mass from rest to its stated velocity. The equation for kinetic energy is 1 half mv squared.
Another relevant concept that we'll be using in the sense making and the calculations symbolically that we're finding is potential energy. The definition for potential energy is that in physics, potential energy is an energy held by an object because of its position relative to other parts of a system. Stresses within itself, its electric charge, or other factors. A spring has more potential energy when it's compressed or stretched. So the potential energy equation is 1 half kx squared. And then one last relevant concept that we'll be using is the law of conservation of momentum. The conservation of momentum states that within some problem domain, the amount of momentum remains constant. Momentum is neither created nor destroyed, but only changed throughout the action of forces as described by Newton's laws of motion. In this problem, we have the two blocks sticking together at some point, so that's going to be where we use the law of conservation of momentum that we will talk about later in the slides where we're solving for it symbolically.
With our representation that we're looking at now, we have 5 boxes total. In those boxes, in the first step, we see is where the blue box is just at rest inside of that spring with potential energy. The red box is not in motion either, and then the other spring is on the other side. The second box we see, the blue box is released and it is going towards the red box. The third box, the blue box and the red box combine and make an inelastic equation collision. And then the fourth box, they're still on that momentum towards that second spring on the other side. And then that fifth box, those boxes have come together and they are pushing against that spring.
Some of the relevant equations that we'll be using is the equation of kinetic energy, which is again 1 half mv squared, and then we will also be using potential energy, which is 1 half kx squared. We also have the law of conservation in this symbolic problem where the initial momentum is going to be equal to the final momentum. And then we have that kinetic energy is equal to the potential energy of the spring. Some of the variables that we'll be using is MB, which is just going to represent the blue box, and then MR, which is going to represent the red box. So the first step to solve for it symbolically, we're first going to start with setting kinetic energy to the potential energy of the spring. We know that the blue box eventually starts moving, so we know that the potential energy needs to convert into that kinetic energy, so we can equal them to each other and solve for the velocity of the blue box. In the second step, we know at this point that the blue box is moving towards the red box that is at rest, so we can set the momentum initially to the final momentum. And what we would do for this part of the equation is we do mb times vb plus mr times vr, which is going to be equal to the final momentum But in this case, since the two blocks, the red one and the blue one, stuck together, we need to add the masses, and then that's just going to be multiplied by the final velocity. In the third step, we have to rearrange the equation to find the final velocity that the two blocks had. And a way that we can do this is we just divide over the mb plus mr onto the other part of the equation. We know that there's no velocity for the red box at the initial point, so we can just cross that part of the equation, and then we just have mb vb over mb plus mr, which is the final velocity. The next step to be able to simplify the final velocity is that we need to add in the initial velocity that we had found for the blue box. We found that in step 1 when we set the potential and kinetic equations to each other. So we just plug that in, and then that's going to be our final velocity equation that we can use for our next steps. So for step 5, now that we have the final velocity, at the beginning we equaled the kinetic energy to the potential energy of the spring that the blue box was on. To find our final answer of the distance that it compressed, we need to do kind of the same idea, but before we do that, we need to find the final kinetic energy so that we can equal that to the final potential energy of the spring. To do that, we just take the kinetic equation. We know it's 1/2 times mass. In this case, the mass is now the two blocks instead of just the blue box. So we add the blue and the red box together for the final mass in this equation. And then we found the final velocity in the previous steps, so we just plugged that in. After we simplify it down a little bit by squaring across and crossing out some of the variables, then we end up with 1/2 mb over mr plus mb kxi squared. If we see at the end the kx squared, that looks a lot like the potential energy equation. So if we wanted to do a unit check at this point, we could, since we know that the masses are going to cross out in units, and then we're just left with energy units at the other side for the kinetic final, and then for the potential on the other side, we just are left also with energy units, which end up just equaling to each other. So that's another good step that we can do to unit check at this point before we get to the final equation. As I mentioned before, to find the last part in step 7, we're going to be equaling the kinetic energy to the potential energy of the spring. We did this in the first part and we were able to find the velocity, but now we're going to be equaling them to find x final, which is just going to be the distance that it compressed. So in this case, once we set them equal to each other, what we can do is just divide over 1/2 k, and that crosses out a few variables. And then since we still have the x squared final, we're just going to square root that across. We end up with the xi square root mb over mr plus mb. That's going to be the final distance that it compressed.
With our unit check, as you can see, our first step is our xf equals xi square root mb divided by mr plus mb. In those terms, we have our final distance, our initial distance, and then our weights of the red box and the blue boxes. Those are all distances or masses. So distances are going to be in meters, while masses are going to be in kilograms. So then we get m equals m square root kilogram over kilogram, which kilogram over kilogram will cancel out. That is just how it goes. And then on the third step, we have meters equals meters. This makes sense with our problem because we're going to have that final distance, but on top of that, we need our answer to be in distance because we're finding the distance of that spring.
All right, my name's Tyson, and I'm here to walk you through some of our reflections. So to kind of start off, we're going to talk about our first similarity, and that is that some similarities that we saw from this problem in class when we were talking about collision being elastic or inelastic. We have done very similar work in the studios before, specifically the combining of the blocks, like the one we did in the week 9 studio labeled prediction. Another reflection that we saw in the similarity category was that we saw in class determining the displacement of springs. we did a lot of that during this problem, which was what we were solving for. And then I worked on this a lot with my group during the capstone lab that we just finished up this week. I specifically remember this one because I had to learn how to do that. And so being able to do that capstone lab really helped solving this with the group. Then the differences in our reflection. So a difference that we saw from this problem from what we saw in class is that this example has the blue block starting from a spring rather than like an external force acting upon the block like we saw in class. I'm comparing this to like activity 6.6-2, 3 bricks 2. It allowed for us to see how it all moved within a system. So with the springs, made it a little bit different, and that was one of the differences that we noticed. So again, thank you for listening to our project 2 for Physics 211, and have a great day. Thank you.